Hello everybody. Today we continue our lecture series on search methods in artificial intelligence. In the first lecture we talked about automated problem solving and we discussed the state spaces that are created. Today we move on to the next topic of state space search. In the first lecture we discussed that there are several complex problems like pathfinding, chess playing, robo assembly, chip design, timetable scheduling, symbolic integration. And all of these require individual problems, algorithms to solve these problems. However, the goal of automated problem solving in artificial intelligence is to enable non-experts to specify the problem so that there is a common methodology to automatically create solutions for these problems. And then we discussed each of these problems in details and we came to the conclusion that for a large class of problems there is a common structure which can enable us to move towards automated problem solving. Therefore, we said that we are interested in generalized techniques for solving large classes of complex problems. The problem statement is the input and the solution is the output. Sometimes even a problem-specific algorithm or method will be the output. And from the various examples that we saw, we said that we can find a common structure to solve this class of problems. For that, we required the following. One is we required the definition of a state. That means the problem instance can be in a particular state. So we need to define the concept of a state or a concept of a configuration. Given the concept of a state or configuration, we need to define what are valid configurations and what are invalid configurations. A configuration or a state is a current instance of that problem as it is now. Then we show that to solve the problem, we can try to use a set of state transformation rules or rules of state change. And there are outcomes. So given a state, whatever it is for a particular problem, there will be a set of rules which enable us to tell us that from this state we can go to these states. So it's a local definition of how from one state we can move to several other states. And this local definition is applicable on every state. It is applicable on every valid state, which means that by this local definition being used again and again, we create what is called the state space. But we do not explicitly generate the state space. This state space is implicitly defined by these state transformation rules. Therefore, the state space generated by these state transformation rules is an implicit state space. Then we are given the initial or start configurations. We are given what are the configurations where a goal condition is satisfied. And this implicit state space is created by the start state, the goal conditions, the definition of the state, and the state transformation rules. Our job now is to find a valid solution from start to the goals. And in order to find a valid solution from start to the goals, we wish to search this implicit state space. But our search method is to be such that we would not like to create the whole implicit state space explicitly, but we would like to intelligently explore the implicit state space using the state transformation rules. That forms the class of search algorithms. So the whole automated problem solving by search methodology, which tries to capture a large class of problems in one paradigm or framework, models them in a concept as mentioned above. Now, there are a lot of major issues. These are very complex problems. Therefore, the size of the implicit state space is huge. You can imagine the size of the state space of a map finding algorithm for all the cities of the world. Or you can imagine the state space for a chess playing program, or a robo assembly, or a VLSI chip design where there are billions and trillions of transistors to be connected. The second important thing which brings in is that every problem has its inherent domain knowledge, and this domain knowledge is to be captured for that particular problem. So while we have general purpose algorithms, these general purpose algorithms must be able to capture and utilize domain specific knowledge for every problem. Finally, we want to have intelligent algorithms that work in reasonable time, memory, and will handle various kinds of things like uncertainty, etc., which we shall come to. So this is the overall framework on which we want to define what is called state space search, because this is methods for searching state spaces, and that is what we concentrate on in this lecture. So to give a little more formal details, the basics of state space modeling involve the following 6 criteria. The first is the concept of a state or a configuration. And for that, we need to formally define a set of variables and what are the valid values for those variables. So we need to define a set of variables, we need to define the domains of every variable, and we need to define a set of constraints amongst variables to define a valid configuration. So we are now slowly moving into a formal definition of the state space. Secondly, we need to define a set of rules, and this set of rules which says that given a particular state, we need to find the valid set of next states for a given state. So given a state, we need to find the valid set of next states. In AI terminology, it is also called moves. The third concept which we have discussed is the state configuration definition and the state transformation rules, which are local rules defined at every state in a compact form. There is this large state space which is now implicitly defined by the state configuration definition and the state transformation rules. So that is called the implicit graph, because in that graph a node is the same as a state, and the edge to create new nodes comes out of the state transformation rules. So from the state transformation rules, we get the edges and we get new states. So by this definition, we create a graph. This is the implicit graph. Then you are given a set of start states and you are given a set of goal definitions by which you can recognize whether a given state is goal state or not. Finally, you have solutions and their costs. Depending on the problem formulation, a solution can be a path or a subgraph. We discussed it a little in the first lecture, and now we will show it in more details. So now, given the costs of a path or a graph or a subgraph or a solution, we are interested to find a low cost, if possible the best cost solution, but we are also interested to find it as quickly as possible by searching the implicit state space as less as possible. That is why we come to what are called the search algorithms. They intelligently explore the implicit graph or state space by examining only a small subset to find the solution. And the second thing is, we mentioned just a little while earlier, is the use of domain knowledge, which means that we try to use domain knowledge, and these domain knowledge in AI terminology is called heuristics. So we now refined our state space modeling concept to a more formal explanation. We saw this two jug toy problem earlier, and we just reiterated how we formulate it in state space. The state definition is by two variables. We have two jugs, as you know, one jug of volume 3 liter, one jug of volume 5 liter. There's a bucket full of water, and we can, given that both are initially empty, we need to find a sequence of moves so that one of the jugs, which is the 3 liter jug, has got 1 liter of water. So we do a state definition. There are two variables, J1 and J2, which defines how much water is there in any variable, in any jug. Secondly, the constraints that are there on J1 and J2, we know that J1 must lie between 0 and 3 as an integer value, and J2 must lie between 0 and 5 as an integer value. Then what are the state transformation rules? We have fill J1, which means that J1 can be filled from the tank. So whatever was J1, J2, this is how it is written, it becomes 3J2 because it is now full. Secondly, fill J2, whatever was J1, J2 now becomes J15 because it is full. Similarly, empty J1 will make J1 0, empty J2 will make J2 0. Then we can pour from J1 to J2. So suppose it was J1, J2, then it will become XY. Either J1 will become empty or J2 will become full, and in between them, whatever is remaining, the total mass balance of water must be the same, and therefore the rules are so defined. We have discussed this. The start state is 0, 0, the goal state is 1, 0, and a part of the state space is shown here, and we have discussed this before. So this is the state space definition of the two jug problem. Let us come to the other problem which we discussed, was the 3-disc 3-peg tower of Hanoi. Here we know that we have, this is the configuration. There are 3 pegs A, B and C and 3 discs. Let us number these discs 1, 2 and 3. That means 1 is the largest, 2 is the second and third is the smallest. A state definition of this can easily be made in many ways. One of the simplest ways is to indicate for A, for B and for C what is the sequence of objects in that peg. For example, if we write 1, 2, if we write nothing is here and we write 3 here, which means that this is equivalent to this configuration, which means that in peg A we have items 1 and 2, in peg B we have none, and in peg C we have 3. And the state transformation rules are very simple. We have move from peg X to peg Y. That means the top disk will move from the peg X and move to the top of peg Y. Now, in a state, the valid configurations are as follows. That means we have said that there are only 3 disks. Therefore, and the valid configuration is that never can a smaller disk be below a larger disk. Therefore, the move also must be taking into account that you take moves from a valid state to a set of valid states. For example, from this state X, we can move to state Y, wherein we move the top disk, this one, to this. We can also move to state Z, which is not mentioned here, which is take this peg and move it to B. By this, we can create the whole state space which is shown here. For example, here we see this is our initial configuration as X. Here we move the smallest disk from peg A to peg B. Here we move it to peg C. Similarly, the valid moves create, this is the implicit state space that is created out of the state transformation rules mentioned in this move operator. And what is our goal state? If our start state is all the disks are properly stacked up in A, our goal state is all the disks can be properly stacked up in C. And we can find out from this state space that this is one solution, this is one solution, and that all the paths that lead from here to here, from the start state to the goal state, this could be the goal state and this could be the start state. In fact, this state space that is defined here, you can put anybody in the start state and anybody in the goal state, and you will get a sequence of paths. Our objective is that this state space may not be provided explicitly. Just from the state transformation rules and the start state and the goal definition, we want to move on to the finding the solution. This 3-disk 3-peg towers of Hanoi is a simple problem, but if we move to an n-disk k-peg tower of Hanoi that we had just discussed, it will become a very large state space. We had also discussed that there are various aspects which are related to states, spaces, solutions, and such. Firstly, we said that the states can be fully and perfectly informed. However, some states could also have partial information. We looked at this control problem which we said. We said that there are many variables in a control plant, but all the variables are not observable, which means that for a given state, all the values of every variable in that state may not be known. So the problem can have partial information. Whereas the Tower of Hanoi or the chess playing problems are having full information. On the other hand, the card playing problem again has partial information because whereas the system has full information, but from a particular player's point of view, there is only partial information. Then the state transformation rules can be deterministic. That means from a given state, these states will definitely happen. So that means if you make a move from one state to another state, that move will exactly happen. But it could also be non-deterministic or probabilistic, and we mentioned this example of a car brake application, where we said that if I apply a car brake, then there is 99.5% chance that the car will stop, but there is a very low chance that the car may not stop because there is a brake failure. We also said that if the partial information is there for a state like a control plant or a card playing game, then when you make a move, then whatever is the outcome is not explicit because you don't know exactly what will happen. And if there are multiple players, then the outcome that comes to you when you want to play again is a little different. Third aspect was how many players are there. The normal state space problem, which is an OR problem, is a single player game. On the other hand, you could have multiple players which are adversarial, collaborators, or probabilistic, and they lead to a different kind of a situation. We also discussed how problems like the plate cutting problem are formed out of composing sub-problems, and therefore a solution is not just a path like in a Tower of Hanoi problem, but is an ANDed solution of sub-problems. So we could have paths, we could have subgraphs, and in probabilistic cases we could have expected outcomes. Then there are costs of solutions. For example, one move may be one cost, but in a plate cutting problem, we could have the free space or the wasted space is my cost. Then the problem sizes, then the domain knowledge and application of search algorithms. This forms the gamut of state space search. Let us come to a classical problem which is called the traveling salesperson problem. The traveling salesperson problem, many of you know, is a set of cities which have got road maps, and the salesperson is to travel from one city covering every other city exactly once and coming back to the original city. This is a very difficult problem. It is known as an NP complete problem. and finding these solutions are very difficult for large sizes, for 1,000, 5,000, 10,000 cities. Even today, the largest computers find it very difficult. For example, here is a toy example of a 5-city traveling salesman problem. There are 5 cities A, B, C, D, and E, and the edge weights on these cities. Here we have connected every city to every other city. It need not be the case everywhere. And between 2 cities, we have marked out the distance or the cost of traveling between them. Now look at the options. If we go from A to B to C to D to E and then go back to A, that is what we want to do, then my costs are 100 plus B to C is 75 plus C to D is 110 plus D to E is 50 and E to A is 190. So this sums up to a cost of 175, 285 plus 50, 335 plus 90 is, I think this comes to 435 and 515. On the other hand, if we take a sequence of A to B to D to E to C to A, then our sequence is 100, 75, 50, 90 and 120, and you can easily see that this is a shortcut path. So the objective here is to be able to find the shortest cost path. So how do we define our state? We define our state definition by 2 parts. A state definition has 2 parts. One is a sequence of states visited till now and a cost. So, 1 minute. So it is a sequence of states visited till now and C is the current cost. For example, if I have done A to B to C, then my state definition would be A, B, C, and my cost would be 100 plus 75, 175 plus 110, which is 285. So this is how I define a state. And if I am given a state, then the state transformation rules are easily defined from this graph. The state transformation rules come from the graph. So given a state, I will extend the state by 1 more city. If I have covered every city, then I go back to the original city. Otherwise, I add another city for which there is a path or an edge in the graph such that that city has not been visited before. So that is how I create from a particular state, I create many new states. And then my start state is when I am in the one of the initial configurations, which may be A, and my goal state is when I have covered every state exactly once and return to the start state. So this is how this traveling salesman problem looks like. We start with A0. Then using the state transformation rules, I can go from A to B, I can go from A to C, I can go from A to D, I can go from A to E. And if I go from A to B, the cost is 100. If I go from A to C, the cost is 120. Depending on the edge cost. From A to D, the cost is 200, A to E. And then again from AB, I can go, if I've done AB, I can go ABC, which is 175, or I can go ABD, which is also 175, or I can do ABE, which is 180 because of the additional costs. Now from ABC I cannot go to ABCB because I need to visit every city exactly once. So from here ABC I have got only two possible successors, ABD and ABE, ABCD and ABCE. Similarly, this whole graph can be created, and at every goal node, for example, this is a goal node because I have done A, B, C, D, E, A. This is a goal node A, B, C, E, D, A, and for each of them I have costs. And this is the implicit graph. We do not generate this graph first a priori, but this is the implicit graph defined by the state transformation rules of the traveling salesman problem. So the traveling salesman problem is an OR problem because there is only one player who finds a sequence of moves, and that is where this player has a choice. But as we have seen in the previous lecture, that there could be multiplayer games, there could be probabilistic situations where if I make a move, the moves made due to the environmental situations are not in my control and any one of a sequence of moves can come, or it could come because of an adversary and various other things, or it could come because I have to solve sub-problems like in the plate cutting problem. So while these are OR nodes where the player who is actually the solver of the problem can make a choice, we have the AND nodes where the player does not have a choice and the player has to take into account scenarios where somebody else makes the choice. Let us see some examples. This is the famous noughts and crosses game. We all know this is the famous noughts and crosses game. And here there are two players, player 1 and then player 2, then again player 1 and then player 2. So player 1, once the player 1 plays, the state is defined by these 9 variables, x11, x12, x13. So this is 9 variables, x11, x12, x13, x21, x22, x23, x31, x32 and x33, and the domains of these variables are either it can be empty or it can be filled by 0 or it can be filled by a cross. The initial state is everybody is empty, and then players play in sequence. The state transformation rules are that whosoever is the player can, if the player is player 1, then the player 1 can apply cross, and if the player 2 has to play, then the player 2 can apply a 0. So based on that you create the implicit state space, and in this implicit state space we notice that this is an OR node. On the other hand, when player 2 plays, then player 1 has got no chance to control what player 2 will do. So this and this are all AND nodes. Again, when player 1 plays, this is an OR node, this is an OR node, and wherever there are terminals, which means that this is a goal state, this is a goal state. Similarly, these two are goal states because in these two states somebody wins. The player who has scored 0, 0, 0 actually wins. So here we create what is called as an AND OR graph or an adversarial graph, where player 1, who is the person solving the problem, has got choice in some nodes, but when player 2 is supposed to play, player 1 has to take into account all the things that player 2 can do. So in general, when we compose, like in the plate cutting problem, when we compose smaller items into a larger item, this AND OR graph has the following structure. The node A, which we have mentioned here, are OR nodes. The node B, which is marked by this sort of a edge, is an AND node. And let us say that these are leaf nodes and they are labeled A, B, C, D, E, F, G, H, I, J, K, L, and M. Then if we are to find solutions, the solution at an OR node, the player can take one direction. But at an AND node, the player who is the OR player, whose choice we are trying to solve, has to look at all options. Therefore, the solution is no longer a path. For example, in this case, one solution will be this, followed by this. You have to take all these into account. Then this is the leaf node. Then here you have a choice, so you can take this choice, and here is a leaf node. Here you can take this choice, but then here both of them are there. So this, followed by this, followed by this, here, 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 and here, this forms one solution. Similarly, you can have another solution. The player 1 could have chosen this path. But once the player 1 has chosen this path, then this AND node all have to be chosen. In this OR node 1, in this OR node 1, and in this OR node 1. But since they have chosen this one, in this AND node, this has to be chosen. Therefore, this is another solution. So the solution to an AND OR graph is an ANDed subgraph. So for an AND OR graph, the solution is not a path but an AND subgraph which leads to terminal nodes. And then, depending on the costs that are there, the costs may be many. Therefore, in some cases when it's composition, at the OR node the cost could be min. At the AND node the cost could be sum, product. And in case of adversaries, the cost could be max, because you have to take into account the worst case scenario for yourself. So based on this, you create costs of solutions to AND OR graphs, and you try to find the minimum cost solution. Let us look at a very interesting problem which we come in algorithm design. We know that matrix multiplication, for example, if I have to multiply 4 matrices M1, M2, M3 and M4, then matrix multiplication being associative, I can multiply them. I can first multiply M3, M4 as shown here, then the result with M2 and the result with M1. Or I could multiply M1 and M2. I could then multiply M3, M4, and I could multiply the results. And there are 2 more ways by which I can do. But the cost of computing this depends on the sequence. Let us look at Y. Let A be a P by Q matrix, and let B be a Q by R matrix, because if they are to multiply, then the second dimension of matrix A and the first dimension of matrix B must match. And because the way the multiplications are needed to compute A into B, we have to find the solution, because the final solution of AB, it is a P by R matrix. So every P by R solution has to be done by a row into column product of Q times, which means that the total number of computations that I have to do to compute a multi-product of matrix AB is P into Q into R. Now let us look at 3 matrices, M1 10 by 30, M2 30 by 5, and M3 5 by 60. Now they can be multiplied in two ways. I can first multiply m1, m2 and multiply the result, or I can multiply m2, m3 and multiply the result. So if I multiply m1, m2, for m1, m2, because it's 10 by 30 and 30 by 5, then I need so much for m1, m2. And then after I multiply m1, m2, then what do I get is a 10 by 5 matrix, which I have to multiply to a matrix of 5 by 60. So I will require 10 into 5 into 60 for this, which is, if I've got P equal to M1, M2, and then P into M3, which will give me 4,500. On the other hand, if I do M2, M3 first, then for computing M2, M3, I require so many multiplications, 30 into 5 into 60 to get Q. And then if I do M1 into Q, I require a 10 into 30 into 60, which gives me 27,000. As you can see, the sequence of multiplications by which I will get the solution needs to be optimized. And for a large size sequence, this can make a huge difference in the total computation time. So how will we find it? So we again model it as an AND/OR problem. And we have two kinds of nodes. The OR node, where we are trying to minimize among options, and an AND node, where we try to break up the problem into subproblems. So in a state definition, at the root is M1 to M4 if we are to do 4 matrices M1, M2, M3, M4. And these M1 into M4 can be done in 3 different ways at this OR node. Now M1 into M4 can be done in 3 ways. What are the 3 ways? I can do this one, which is I can leave M1 and then do M2 to M4 and then find the composition. So this I'll get as P, this I'll get M1, this is M1 and this is Q, and I will do M1 into Q. So I will get Q back here and this M1 into Q will be done. Or I could use this option, which is M1, M2 into M2, M3, and I will get this and this. Or the third option is I can do M1 into M2 into M3 and multiply it by M4. And I have my fourth option, which is this, which I have not drawn. So I will have the fourth option. So based on this, I have these are my AND nodes. Again, this is an OR node. I can do it in many ways. M1 is a leaf node. It does not require anything to be done. On the other hand, M2, M4 will again have 2 options, and so on and so forth. And this gives me my AND/OR graph, and the solution to this AND/OR graph is obtained by any one solution will be taking one direction in an OR node and both in an AND node. Again, one in an OR node and both in an AND node. So this is how I will get an ANDed subgraph. Each ANDed subgraph will give me a solution. The cost at an AND node is defined by the cost which we have just defined in terms of matrix multiplication. The cost at an OR node, where I want to take the minimum of these 3, will be defined as a minimum. Therefore, there is a function definition of P into Q into R, which defines the cost at an AND node and a min at an OR node. And this gives us an AND/OR graph. So as we have discussed earlier, the searching of these implicit graphs is not done by first making the whole implicit graph explicit. So we start with the start node and then we intelligently create successors. And then we choose one of the successors and again create some more successors in our attempt to very quickly reach the goal node without generating the complete state space. And for OR nodes, we have a path which is the goal, start to goal, and in an AND node, obviously, it consists of the subgraph, and the cost is defined in many ways. For a path, a typical way is sum of the path costs. And in AND OR graphs, as we have just explained, the cost of an OR node is either min or max, and the cost at an AND node depends on whether it's a compositional, adversarial, or probabilistic. In game trees, where there are two-player games, then for the player for whom we are designing, n is a min because we try to define leaf node as a win as the best cost, as a loss as the worst cost, and a draw as something in between. For example, we say that if I win, then I get a -1, and if I lose, I get a +1, and if I draw, I get a 0. So for a particular player whom I want to win, then I will make min at the OR node, and at the opponent's node, I will try to take the max because that is the opponent will try to worsen my situation. Now, what are the search algorithms that we use for developing this? Today we will discuss the basic search algorithms, which is depth first search, breadth first search, and iterative deepening. Later on, we will discuss more complex search algorithms. So the depth first search, there are two lists which we use. One list is called the open list, and one list is called the closed list. The open list consists of all the states which we have made explicit but not made its own children. The closed list are those nodes whose successors have been already generated and put back into the open list. So we put initially the start node in the open list, and the closed list is empty. The goal testing function is so the whole algorithm proceeds in the following way. We initialize the open list with the start node. We select the first node in the open list, the first node. If open is empty, then obviously there is nothing else to see, so we terminate. Now if this node that we have taken out from the open list is the goal node, we terminate. We can continue the search as we shall see, or we can terminate. If it is not a goal node, then for this node that we have taken out of the open list, we create its successors, n1, n2, n3, and so on and so forth. We put n back into the closed list. And for each of its successors, which is not already in the open list, we put it in front of the open list, which means that we are now treating the open list as a stack, as a stack data structure. And for each ni which is already on the open list, then there is a sequence. For the time being, we will do nothing. And then once we have done this, we go back to step 2. Again, we take a node out of the open list and we continue in this process. So if we continue in this process, we are creating what is called the depth first search algorithm, where we systematically explore the state space. A variation of the depth first search algorithm is called iterative deepening search. While the depth first search algorithm has a problem of going in one direction deep, whereas the solution may be lying somewhere else, iterative deepening does DFS iteratively, which means it performs DFS level by level. It first performs DFS for level 1, then it performs DFS for level 2, and so on and so forth, which means that it performs depth first search up to level 1, then it performs depth first search up to level 2, then it performs depth first search up to level 3, and so on. So if this was the state space that is generated, Then it would do DFS up to level 1, then DFS up to level 2, and so forth. We'll see the clear examples as we move ahead. So it restarts, but it has the advantage, as we shall see later, of not going blindly in one direction like depth first search. The third approach that we have is called breadth first search. In breadth first search, the only difference between depth first search and breadth first search is that the open list is now treated as a queue. If you recall, in depth first search, we were putting it at the front of open, which means that it was working in a first in, first out mode. And it was moving in a first in, first out mode like a stack. Whereas in breadth first search, it is the first in, last out, which means that it is moved to the end of the queue. That is the only difference, and we shall see how it varies. So let us look at this example. Let us look at an example where the explicit graph has got A, B, C, D, E, F, G, H, I, J as the nodes. A is the start node, and I, J, and H are the goal nodes. Let us see. The red arrow, as you can see, is a back edge from a goal to C, just for making the algorithm interesting, so that there is a loop in the graph. So let us see how the algorithms that we have mentioned now work. So first we will see depth first search. In depth first search, initially open consists of A and closed is null. This is this state. So the algorithm says remove the first node from open. So we remove A and put it in closed. And we generate the children of A, which is B, C, and D. So A is put in closed, B, C, and D are generated and put in open. Next, again we repeat, because we now take out B from open, because it is the first node in open, and we put it in closed. So closed becomes AB, and because B is not a goal node, we generate the children of B, which is E, F, and G, and we put it in the front of open. So open, which had got B, C, D, and then B removed, it had C, D, now has got E, F, G, C, and D. Then again, we remove the first node from open, which is E. And once we remove the first node from open, we put E in closed. And we generate children, and among the children are I and J. So now they are put in front of the queue. So now we have, when E was removed, so F, G, C, and D were there in open, I and J are put in front. And then we remove I, and I being a goal node, as per the algorithm, if the node removed from open is goal, you can decide on termination. So we could terminate here, and we could terminate with this as my path, solution path. On the other hand, if we want to find the shortest cost path, because as you can easily see, the shorter path is from A to D to H, and depth first search will not find the shortest cost path. Therefore, we can continue the search and try to update the cost of the best cost path and terminate with the shortest cost path. So that would continue depth first search. So depth first search could terminate at the first goal, or it could continue for run. So depth first search also has a very low memory requirement, as we shall see, because the size of the open list will be contained by the depth of the search. And as soon as the search backtracks from its particular depth, we will see that the size of the open list starts reducing. But if the graph is potentially infinite because the state space is defined by implicit set of rules, then it can just go on and on in one direction and never terminate. So this is the basic depth first search algorithm. Let us look at iterative deepening. Iterative deepening will first start and do depth first search but backtrack from level 1. So it will first visit this node, then it will not generate these children because it is backtracking from level 1. Beyond level 1 it will not do. So if it reaches a node of level 1, it will not generate its successors. So it will first generate node 1, then node 2, B, node A, B, then C and D and terminate. It will not come up with a solution at iteration 1. Then it will move to iteration 2, and in iteration 2 it will restart. And it will restart, again it will expand this 1, 2, it will go to, it will do this is the sequence of nodes which will be expanded. Now from this node and this node it will not go further. Then it will come back and do node C. Then from node C there are 2 children, but they are already done. It may do it again, it may not do it again depending on the algorithm. Then it will come to node D and expand this as the 6th node. This was the 5th node. So this was 4, this was 5, this was 6, this will be 7. And from D, again it will go to G, which is already done, and this node, and finding this as the goal, it will terminate. So it will not go to level 3 at all. As you can see, depth first iterative deepening repeatedly does depth first search. So it performs depth first search to level 1, no solution found, then level 2, and a goal H is found. So it will terminate with this path A, D, H after the second iteration. This is guaranteed to find the minimum cost path. While it repeatedly re-expands nodes in different iterations, it may re-expand nodes, but it guarantees the shortest cost path to goal. And it has a lower memory requirement than breadth first search and a very similar memory requirement as depth first search. The third algorithm which we shall discuss, which we have briefly mentioned earlier, is breadth first search. The difference between depth first search and breadth first search is the fact that in breadth first search we put the newly generated nodes at the end of the queue, not at the beginning. So let us see how it works in this example. We start with node A. So open consists of node A and closed is empty. Then from A, we put A in closed and generate children B, C, and D and put it in open. Up to here it is same as breadth first search. Then again, now we remove B, put B in closed, and we generate children E, F, G. But in depth first search we were putting E, F, and G in front of the queue. Now we put E, F, and G at the back of the queue. We were putting it in front of open, now we put it at the end of open. So now the sequence changes. So after A is done and B is done, the next node that is removed is C. So C will be removed, C will be put in the closed queue, and the children of C are already in open, so nothing happens. So the queue now open list becomes D, E, F, G. Then D is removed, so the closed list becomes A, B, C, D, and D has 2 children, which is G and H, of which G is already existing, so H is put at the end of the queue. Then node E is expanded, and from E we have got these 2 children of E, and these 2 children I and J are again put at the end of the queue. Now F is in front of the queue, so F is removed. F has children I and G, but they are already in open, so nothing is added to the queue, and the queue becomes GHI. And then G is removed and its successors are put, and its successors are already in open. So we have H, I and J, and closed is this large list. Now H is removed next, and being the goal node, it is terminated. We can see that the breadth first search guarantees the shortest length path to goal, but as we shall see, because it moves in a breadth first manner, it has a much higher memory requirement than depth first search or iterative deepening. So these are the three basic search algorithms that we have, and then we will expand and improve on these algorithms. Now, as we have said that the search space may have costs. So our goal will now be to find the best cost path from start to goal in the implicit graph. Obviously, we really do not want to generate all the nodes. In the examples that we saw, as you saw, depth first search did not generate all the nodes. However, breadth first search did. Iterative deepening also did not try to generate all the nodes, but it did in this case. And we shall see how we can avoid generating as many nodes as possible. So our goal will be to modify these algorithms. And in order to modify these algorithms, we need to now take into account at every node n a value called gn, which is the cost of the path or the current path from S to n. And we will have to use this gn value to order the nodes. For example, when we use depth first search and we put it in the front of the queue and we find the first goal node, if we terminate at the first goal node, then that may not be the optimal cost. So we may have to continue the search to try and do a branch and bound to try and update the costs. On the other hand, in breadth first search, instead of putting it at the end of the queue, we will now have to convert open list to be a priority queue to be ordered by the GN values. And similarly, we will have to update iterative deepening algorithm. So based on this, for cost ordered search, we will get depth first branch and bound. For breadth first search, we will convert it to what is called best first search. And for iterative deepening, we will convert it to best first iterative deepening search. While we look at this, we will now see how we can use heuristic estimates or problem specific information. And that is what we shall do in the next lecture when we talk about heuristic search. Therefore, as a summary, we have seen in the first lecture how automated problem solving can be converted into a state-based state transformation problem leading to ordinary OR graphs and AND OR graphs. Then we have seen how several problems can be modeled using the state transformation rules. And the basic search algorithms involve exploring and slowly making explicit the search space by using basic algorithms by depth first search, iterative deepening depth first search, and breadth first search. Then we saw that there may be costs involved and domain specific knowledge involved, and that leads us to the next stage of algorithms, which is called heuristic search algorithms for automated problem solving in AI, which we shall do in the next lecture. Thank you very much.